Hello students, today I'll revise second PU chemistry for PU board examination. Important questions I'll explain first. First one, derivation of integrated rate equation for zero order reaction, or derive an expression of rate constant for zero order reaction. Consider a zero order reaction, reactant gives rise to product. According to rate law, rate is equal to K into R to the power of 0. Another one, rate is equal to minus dr by dt. dr by dt. Here R to the power of 0, R to the power of 0 is equal to 1. That's why rate is equal to K. When you substitute this, then we'll get K is equal to minus dr by dt. When you rearrange this equation, we'll get dr is equal to minus K into dt. For this, integrate both the side. When you integrate both the side, then we'll get integration dr is equal to minus K into integration dt. So here integration and difference will get cancelled. Then r is equal to minus kt plus I. Here I is equal to integration constant. At time 0, r is equal to r naught. Therefore, r naught is equal to I. Substitute I value in equation 1. That is this one. So now when you substitute I value, then we will get r is equal to minus K into t plus r naught. Here I is there, no, in the place of I, we are going to take r naught. Then separate K term, then we'll get K is equal to r naught minus r by t. It is integrated rate equation for zero order reaction. Next one, for first order reaction. Consider a reaction, first order reaction, reactant gives rise to product. Here R is reactant. According to rate law, rate is equal to K into R to the power of 1. Here 1 because it is a first order reaction. It is a first order reaction, that's why power 1. Then another one, rate is equal to minus dr minus rate is equal to minus dr by dt. Substitute this one in this expression, then we'll get minus dr by dt is equal to kr. Rearrange this equation, then we'll get dr by r is equal to minus k dt. Integrate on both the sides, then we'll get integration dr by r is equal to minus integration dt. So here integration dr by r is equal to ln r. In the place of integration dr by r, we are going to take ln r. Minus integration and difference will get cancelled, then into t plus I. Here I is equal to integration constant. So at time 0, then r is equal to r naught. Okay, when you substitute these two values in this expression, then you will get ln r is equal to minus k into time 0, r is equal to r naught, then plus I. K into 0, 0, then ln r naught is equal to I. Substitute I value in equation 1, then we'll get ln r is equal to minus kt plus ln r naught. So now simplify this one, then just take minus kt left side become plus kt ln r naught. So ln r naught right side become minus ln r naught. Rearrange that, we'll get k is equal to minus 1 by t ln r naught by r. So here ln r naught by r, that is equal to 2.303 log r naught by r. Then we'll get k is equal to 2.303 by t log r naught by r. It is a first order reaction. Next one, manufacture of potassium dichromate K2Cr2O7. K2Cr2O7 from chromate ore, that is FeOCr2O3 or FeCr2O4. When iron chromate undergoes oxidation in the presence of Na2CO3, forms sodium chromate Na2Cr O4 and Fe2O3 CO2 subproducts. That is step 1. In step 2, Na2CrO4 sodium chromate undergoes acidification, gives rise to sodium dichromate Na plus and H2O subproducts. In step 3, sodium dichromate. It is sodium dichromate. So sodium dichromate treated with KCl gives potassium dichromate. Next, preparation, manufacture of potassium permanganate from pyrolusite, that is MnO2. When MnO2 undergoes oxidation in the presence of base KOH, gives rise to potassium manganate, that is K2MnO4, and H2O as a subproduct. So in this K2MnO4, remove 2 potassium, then we'll get MnO4 minus 2. MnO4 minus 2 undergoes acidification. MnO4 minus 2 is manganate. So manganate undergoes acidification, gives rise to permanganate, MnO4 minus MnO2 and H2. Difference between manganate and permanganate, charge. Minus 2 is there, that is manganate. Minus 1 is there, permanganate. Next, another question, applications of EBT from coordination compounds. From coordination compound, so NiCl taken 4 times, whole to the power of minus 2. Tetrachloridonickelate 2 ion. So for this we are going to explain hybridization, geometry and magnetic property. So oxidation state of nickel is +2, Na2 plus electronic configuration for that. So argon 4s0 3d8. So orbital diagram, so 3d8, 8 electrons, 4s0 4p0. Cl minus is weak ligand, unpaired electrons do not pair up. Okay, so electrons fill in the orbitals according to Hund's rule. Now 3d 4s 4p. So now these 4 empty orbital undergoes hybridization, forms 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals filled by electrons donated by 4 Cl minus ligand. Then hybridization is sp3, geometry is tetrahedral. Magnetic property, here there are 2 unpaired electrons, that's why paramagnetic, due to the presence of 2 unpaired electrons. Next one, NaCN taken 4 times, whole to the power of 2 minus. Tetracyanidonickellate 2 ion. Oxidation state of nickel here also same, +2. Electronic configuration, so argon 4s0 3d8. Orbital diagram 3d 4s0 4p0. Cn minus is strong ligand, unpaired electrons gets paired. So here electrons enters into orbital against Hund's rule. So that's why electrons will pair in this d orbital. We get 1 empty d orbital, 1 4s and 3 empty p orbital. Out of 3, 2 only involves in a hybridization. So total 4 empty orbitals undergoes hybridization, forms dsp2. Why? Because here d orbital, s orbital, 2 p orbital, that's why dsp2 hybridization. 4 dsp2 hybrid orbitals filled by electrons donated by 4 Cl minus ions. So that's why hybridization dsp2, geometry square planar. Magnetic property, observe here carefully, no unpaired electrons, that's why diamagnetic property. Another one is COF6 3 minus. Hexafluoridocobaltate 3 ion. Oxidation state of cobalt is +3. Electronic configuration argon 4s0 3d6. Orbital diagram 4s 4p and 4d0. So here 6 required, 1 4s 3 pp 3 4p and 2 4d. So these 6 empty orbital undergoes hybridization, forms 6 sp3d2 hybrid orbital. So these 6 sp3d2 hybrid orbitals takes electrons from F minus ligand, forms coordinate covalent bond. That's why hybridization is sp3d2, geometry is octahedral. Magnetic property, so observe here there are unpaired electrons, 1 2 3 4 4 unpaired electrons, that's why it is a paramagnetic nature. Next one, CONH3 taken 6 times whole to the power of 3 minus. Hexaamine cobalt 3 ion. Oxidation state of cobalt is +3. Electronic configuration argon 4s0 3d6. So orbital diagram 3d contains 6 electrons, 4s0, 4p0, 4d0. So NH3 is a strong ligand, unpaired electrons get paired. Electrons enters into various atomic orbitals against Hund's rule. So pairing takes place first. Then empty orbitals, 2d orbital, 1s orbital, 3p orbital, d2 sp3. Total 6 hybrid orbitals. What are those? sp2 d2 sp3 hybrid orbitals. 6 d2 sp3 hybrid orbitals filled by electrons donated by 6 NH3 ligands. That's why here hybridization is d2 sp3, geometry is octahedral. Magnetic property, observe here there is no unpaired electron, that's why it is diamagnetic property. Next, SN1 reaction, substitution nucleophilic first order reaction. Hydrolysis of tertiary butyl bromide with aqueous NaOH gives tertiary butyl alcohol. It involves in two steps. Step 1 is formation of carbocation. So in this reaction, so tertiary butyl bromide undergoes cleavage. Cleavage of C-Br bond takes place, then forms a carbocation, positive charge on carbon. Don't ignore to mention positive charge on carbon, that is tertiary butyl carbocation. And this step, formation of carbocation, is slow step, and reverse and also rate determining step. Next, step 2, attack of nucleophile. So here OH minus is a nucleophile, will come from the NaOH. So OH minus will attack the carbocation, C plus forms tertiary butyl alcohol. So rate is directly proportional to the concentration of only alkyl halide. Why? Because it is a it involves in two steps. Step 1 is rate determining step. In that only reactant tertiary butyl bromide. That's why it is a first order reaction. Rate is directly proportional to K into alkyl halide. Rate does not depends upon concentration of NaOH. Next, SN2 reaction, substitution nucleophilic second order reaction. Hydrolysis of methyl chloride. Observe carefully, for SN1 reaction we are going to take tertiary butyl bromide. For SN2 reaction we are going to take methyl chloride. Few students will take methyl chloride for SN1 and tertiary butyl bromide for SN2. Don't confuse. SN2 always methyl chloride. So methyl chloride take or methyl bromide. By taking only these two, you are going to explain SN2. Next, here also SN1, you are by taking tertiary butyl bromide or tertiary butyl chloride. Take any one out of these two. Don't take methyl chloride and bromide for SN1. SN2, take CH3Cl and CH3Br. When methyl chloride undergoes hydrolysis with NaOH gives methyl alcohol. So mechanism, it involves in only one step. Nucleophile OH minus attack the carbon from the backside of the leaving group Cl minus and forms a transition state. The Cl minus is completely removed to give product methyl alcohol. This reaction is inversion of configuration, means product configuration is completely opposite to the reactant configuration. See here, in a reactant Cl right side, but in a product OH left side. That's why it is inverse of configuration. So OH minus will come and attack the backside of the chlorine. Then we'll get a transition state in which partially bond breaking and making takes place simultaneously. After some times, immediately chlorine goes away from the molecule and OH forms complete bond with carbon, forms alcohol. Here the rate of reaction completely depends upon rate of concentration of alkyl halide as well as nucleophile OH minus. That's why it is a second order reaction. Rate is directly proportional to concentration of alkyl halide and nucleophile OH minus. Next, mechanism of dehydration of ethanol to ethene. Protonation of alcohol. It involves in three steps. Step 1, protonation of alcohol. Ethanol CH3CH2OH takes H plus ion from an acid, forms protonated alcohol OH2 plus. Step 2, formation of carbocation. It is the slowest step and hence it is rate determining step. Remove OH2 plus forms positive charge on the carbon, that is carbocation. It is a slow step and rate determining step. Here H2O is a subproduct. Step 3, elimination of proton from the carbocation, which is obtained in step 2. Take that, remove the hydrogen from the carbon atom that is next to the positive charged carbon. Remove this hydrogen, will get double bond between these two carbon atom, that is ethene. Next question, next very important question, mechanism of addition of HCN to aldehydes or ketones. So when you add HCN to the aldehyde, will get cyanohydride. First HCN reacts with OH minus, forms Cn minus and H2O. Cn minus will act as a nucleophile. First nucleophile will come and attack the carbonyl carbon, then pi bonding electrons will shift on the oxygen, forms intermediate, tetrahedral intermediate. Later protonation takes place, add proton, O minus takes the H plus, forms OH group. Cn and OH are attached to one carbon, that's why it is known as cyanohydrine. Now I am going to explain chapter wise important questions. First chapter is solution. Let me explain few basic concepts in solution chapter. First, binary solution. What is binary solution? A solution which contains only two components is called binary solution. Saturated solution. What is saturated solution? A solution in which no more solute can be dissolved. A solution in which no more solute can be dissolved at the same temperature and pressure. Molarity. What is molarity? Define molarity. They will ask. Number of moles of the solute dissolved in 1 liter of the solution. Molarity is temperature dependent. Molarity of solution decreases with increasing temperature. Molarity is inversely proportional to temperature. Molality, LITY, number of moles of solute dissolved in 1 kilogram of the solvent. Don't confuse. Few students will write the definition and interchange the definitions for molarity and molality. Molarity RITY, molality LITY. For RITY, number of moles of solute in 1 liter of the solution. For molality, 1 kilogram or 1000 gram of solvent. Don't confuse here, 1 liter of solution, here 1000 gram or 1 kilogram of solvent. Factors influencing the solubility of gases in liquid. First one is temperature. Obviously you know solubility of a gas in liquid decreases with increase in temperature because of solubility of a gas in liquid is exothermic. Pressure, the solubility of gas in liquid is increases with increasing pressure. Solubility is directly proportional to pressure. Henry's law. The partial pressure of a gas in vapor phase is directly proportional to the mole fraction of gas in the solution. The partial pressure of a gas P is directly proportional to mole fraction of a gas in solution. P is equal to Kh into mole fraction. Here Kh is Henry's law constant. P is partial pressure of the gas, X is mole fraction of gas. Higher the value of Kh, lower the solubility of gas. Solubility of gas. Important, mention this point. Higher the value of Kh, lower will be the solubility of gas. Applications of Henry's law. It is also important. To increase the solubility of carbon dioxide in soda bottle and soft drinks. Bottles are sealed under high pressure of carbon dioxide. Oxygen cylinders carried by sea divers are filled with air which is diluted with helium to avoid risk of bends. Raoult's law for liquid solution, two liquid solutions. For a solution of volatile liquids, the partial vapor pressure of each component of solution is directly proportional to its mole fraction in the solution. Once again I'll repeat. For a solution of volatile liquids, the partial vapor pressure of each component of solution is directly proportional to its mole fraction of the solution. Next question, difference between ideal and non-ideal solution. First point in ideal solution, it obeys Raoult's law at all concentration. Does not obeys Raoult's law at all concentration. Enthalpy of mixing 0. Enthalpy of mixing not equal to 0. Here difference in volume on mixing 0. Difference in volume on mixing not equal to 0 for non-ideal solution. Examples: ideal solution benzene plus toluene, N-hexane plus N-heptane. Example for non-ideal solution acetone and ethanol, acetone and chloroform, acetone and carbon disulfide, phenol and aniline. Differences between non-ideal solution shows positive deviation from Raoult's law. Non-ideal solution shows negative deviation from Raoult's law. For positive deviation, enthalpy of mixing, change in enthalpy of mixing is greater than 0. For non-ideal solution, change in enthalpy of mixing less than 0. Enthalpy of change in volume on mixing greater than 0 for positive deviation. Change in volume on mixing less than 0 for negative deviation. Deviation shown by some binary solutions. Non-ideal solution ethanol positive deviation, ethanol and acetone positive deviation, acetone and carbon disulfide positive deviation, acetone and chloroform negative deviation, phenol and aniline negative deviation. Azeotropes or azeotropic mixture. Binary mixtures having the same composition in liquid and vapor phase and boils at constant temperature. Two mixture of two liquids have same composition in liquid and vapor phase and boils at a constant temperature. Azeotropic mixtures are classified in two types: minimum boiling azeotrope and maximum boiling azeotrope. Minimum boiling azeotrope means the solution which show large positive deviation from Raoult's law from form minimum boiling azeotrope. Example for minimum boiling azeotrope: 95% of ethanol and 5% of water by volume. Maximum boiling azeotrope, the solutions which show large negative. Maximum means negative. Large negative deviation from Raoult's law form maximum boiling azeotrope. Example: 68% nitric acid, 32% of water by mass. Here it is by volume. Osmosis, the spontaneous movement of solvent molecules from the solution of lower concentration to the solution of higher concentration through a semi-permeable membrane is called osmosis. Semi-permeable membrane, the membrane which allows the solvent molecules to pass through it but not solute particles is called semi-permeable membrane. 0.9% weight by volume percentage of NaCl in water is called normal saline solution. Osmotic pressure, the pressure to be applied on the solution of higher concentration just to stop osmosis. Next, isotonic solutions. Isotonic solution means two solutions having same osmotic pressure at a given temperature called isotonic solutions. So now 0.9% weight by volume percentage of NaCl is isotonic with red blood cell RBC. So now isotonic solutions are classified into two types. One is hypotonic, another one is hypertonic. First one is hypertonic, another one is hypotonic solution. Hyper means a solution having higher osmotic pressure with respect to other is called hypertonic solution. Hypotonic solution means the solution having lower osmotic pressure with respect to other is called hypotonic solution. When blood cells are placed in a solution containing more than 0.9% of sodium chloride, the size of the blood cell decreases, shrink. When blood cells are placed in solution containing less than 0.9 mass by volume percentage of sodium chloride, size of the blood cell increases, swell. When blood cells are placed in 0.9% of sodium chloride remains same, no change in the size of blood cell. Why? Because here no osmosis. Reverse osmosis, the process of reversing the direction of osmosis by applying the pressure higher than osmotic pressure to the solution of higher concentration is called reverse osmosis. Applications of reverse osmosis: desalination of CA1. Want of factor defined as the ratio of normal molar mass by abnormal molar mass. Want of factor denoted by I value unity. Conclusion: I value 1, neither association or dissociation of solute. If I is greater than 1, then dissociation takes place. If I is less than 1, association takes place. Yeah, I is less than 1, association; greater than 1, dissociation. Want of factor value for different solutions. For KCl 2. For ethanoic acid in benzene 0.5. Less than 1 means association takes place. Aqueous NaCl 2 MgSO4 3. Why? Because MgSO4 gives Mg2 plus and 2 moles of MgSO4 2, 1 mole of SO4 2 minus. K2SO4 gives 3, want of factor 3 for K2SO4 because 2K plus and 1 SO4 2 minus. Graph shows elevation in boiling point of solvent, depression freezing point of solvent. So the graphical representation: vapor pressure versus temperature. So here TB naught, vapor boiling point of pure solvent. Here TB is vapor boiling point of solution. Here TF is freezing point of solution. TF naught is freezing point of pure solvent. Difference is delta TF. Here difference is delta TB. Problems based on colligative properties. First one is 4 type of colligative properties we have. First one is relative lowering of vapor pressure. Mathematical expression P naught minus P by P naught is equal to weight of solute by molecular weight of solute into molecular weight of solvent by weight of solvent. Here P naught is vapor pressure of pure solvent, P is vapor pressure of the solution. Next one is osmotic pressure. Pi is equal to weight of solute by molecular weight of solute into R into T into 1000 by V in ml. Here R is 0.0821 liter atmosphere per Kelvin per mole, or 0.083 liter bar per Kelvin per mole volume of the solution. V is volume of the solution. Next colligative property: elevation in boiling point. Delta TB is equal to TB minus TB naught. Kb constant, weight of solute by molecular weight of solute W2 by M2 into 1000 by weight of solvent in grams. TB naught be the freezing point of the pure solvent and TB be the freezing point of the solution. Kb is the boiling point elevation constant or molar elevation constant or ebullioscopy constant. Fourth colligative property is depression in freezing point. Delta TF is equal to TF naught minus TF, that is equal to Kf into weight of solute W2 into 1000 by molecular weight of solute into WT1 weight of solvent, that is also in grams. TF naught freezing point of pure solvent, TF is freezing point of the solution, Kb is constant, molar depression constant or cryoscopic constant. W2 is mass of solute, M2 is molar mass of the solute, WT1 is mass of solvent. That's it about solution chapter. Next chapter, electrochemistry. Electrochemistry: differences between metallic or electronic conductors, ionic, electrolytic conductors. Conduct electricity due to movement of electrons. Here under electrolytic conductors, conduct electricity due to movement of ions. Conduction takes place in solid state. Here conduction takes place in molten or aqueous solution. Under metallic conductors, metallic conductance decreases with increasing temperature. Under electrolytic, ionic conductance increases with increase in temperature. Factors affecting the electrolytic or ionic conductance: the nature of the electrolyte, the concentration of the electrolyte, temperature. Factors affecting the electronic or metallic conductors: number of valence electrons per atom, nature of the structure of metal, nature and structure of the metal, temperature. Cell constant G star, the ratio of the distance between the electrodes L to the area of cross section A of electrode. Cell constant L by A. Take a electrolytic cell, two metallic rods connected to the battery and electrolyte. The distance between these two electrode is L, and the area of cross section of the electrode is, when you take a ratio, distance between two electrodes and area of cross section of electrode, ratio of these two will give cell constant. Specific conductance or conductivity: the specific conductance is conductance of 1 meter cube of electrolytic solution. Unit is Siemens per centimeter. On dilution, specific conductance decreases because on dilution number of ions per unit volume decreases. Hence specific conductance decreases. Molar conductance or molar conductivity: conductivity due to all ion present in 1 mole of electrolytic solution. Unit Siemens meter square per mole. On dilution decreases in concentration. On dilution means decreases in concentration. Molar conductivity increases. Kohlrausch law of independent migration ions: limiting molar conductivity of an electrolyte is the sum of individual contributions of cation and anion of electrolyte. For example, limiting molar conductance of NaCl is equal to sum of cation and anion. Cation is Na plus and Cl minus. Limiting molar conductance of cation and anion. Applications of Kohlrausch law: calculations of, first point, calculations of molar conductivity at infinite dilution for weak electrolyte from experimentally determined values of lambda m naught of suitable strong electrolyte. Determination of degree of dissociation and dissociation of constant weak electrolyte. Electrolytes, take a tabular column. Products of electrolysis of some electrolytes. Electrolytes at product at cathode, product at anode. When you take molten NaCl, product at cathode is sodium, at anode is chlorine gas. Aqueous solution, product at cathode hydrogen gas, at anode chlorine gas. When you take sulfuric acid, dilute sulfuric acid H2SO4, product at cathode hydrogen gas, at anode oxygen gas. When you take concentrated sulfuric acid, product at cathode hydrogen, at anode S2O8 2 minus. Next, Faraday's first law of electrolysis. During electrolysis, the mass of substance deposited at electrode is directly proportional to quantity of electric charge passed through the electrolytic solution. Faraday's second law: when the same quantity of electricity is passed through solutions of different electrolytes, the mass of the different substance deposited at the electrodes are directly proportional to their respective equivalent mass. Faraday, the total charge carried by 1 mole of electrons. Reduction or oxidation charge required: 1 mole of Cu2 plus 2 Cu, Zn2 plus 2 Zn, Mg2 plus 2 Mg, 2 Faradays required. In coulombs, 2 into 96,500, that is 1,93,000. Why? Because plus 2 charge converted to 0. Al3 plus 2 3 Faradays. MnO4 minus 2 Mn 5 Faradays. Why? Because MnO4 here, MnO4 2 MnO4 2 plus students. MnO4 to MnO4 2 plus. Why? Because in MnO4 plus 7 charge, in Mn2 plus 2 charge, plus 7 changes to plus 2. That's why change in oxidation number 5. That's why 5 Faradays required. 1 mole of H2O2 O2, 2 Faradays required. 1 mole of FeO2 Fe2O3, 1 Faraday required. Why? Because oxidation of iron changes from plus 2 to plus 3. Change in oxidation number only 1. That's why 1 Faraday required. Daniell cell, a galvanic cell in which the negative electrode is zinc and positive electrode is copper, is called Daniell cell. Anode, zinc undergoes oxidation, copper undergoes reduction. Zinc loses 2 electrons, convert to Zn2 plus. Copper gains 2 electrons, converts to Cu. Overall reaction of Daniell cell, Zn plus Cu2 plus gives rise to Zn2 plus and Cu. Symbolic representation of Daniell cell is Zn single vertical line, Zn2 plus aqueous state, double vertical line, Cu2 plus single vertical line, Cu. Cu2 plus aqueous, Cu in solid state. Functioning of Daniell cell when external voltage is applied against the cell potential, EMF of the Daniell cell. Case 1. If external potential less than 1.1 volt, then electrons flow from zinc to copper, current will flow from copper to zinc. If external potential, okay, external voltage is greater than 1.1 volt, then electrons flow from copper to zinc and current flow from zinc to copper. If external current voltage is equal to 1.1 volt, no flow of electrons and current and no chemical reaction takes place, no redox reaction takes place. Corrosion of iron, rusting we will call it as. Electrochemical phenomenon it is. When the iron is exposed to moist air for long time, brown coating of hydrated ferric oxide formed on surface of iron. This phenomenon is called rusting. Reaction during rusting of iron. Iron will act as a anode, undergoes oxidation, converts to Fe2 plus. Cathode, O2, oxygen and H plus, 4 electrons, converts to H2O. Hydrated ferric oxide is called rust. Composition of rust is Fe2O3 plus XH2O. Methods for prevention of corrosion. Coating of the surface of metal by paint, oil or some chemicals like by bisphenol. Cover the surface of object by other metals like tin, zinc and etc. Next concept in electrochemistry, fuel cell. What are fuel cell? Fuel cell are galvanic cell which are generate the electrical energy by combustion of fuels like methane, hydrogen, methanol, etc. Reaction at anode and cathode of H2O2 fuel cell. At anode, hydrogen reacts with OH minus, forms H2O and 4 electrons. Oxidation takes place. At cathode, O2, 2 moles of H2O. Oxygen takes 4 electrons in the presence of water, forms 4OH minus. Overall cell reaction in H2O2 fuel cell, H2, 2H2 plus O2 gives rise to 2H2. Diagram of H2O2 fuel cell. Yeah, it is a complete diagram. Observe carefully. So it is anode, cathode, exit for water, inlet hydrogen and oxygen. Here aqueous electrolyte, that is KOH. Standard hydrogen electrode, very important. Standard electrode potential of hydrogen electrode is 0. Electrode reaction H plus E electrons gives rise to half moles of hydrogen gas. It is the diagram of standard hydrogen electrode. Symbolic representation of SHE is platinum single vertical line hydrogen, single vertical line H plus, aqueous solution of acid, concentration is 1 mole. The pressure of hydrogen gas in SHE is 1 bar. The concentration of hydrogen ion in the solution is 1 molar. Electrode potential. A potential difference developed between the electrode and electrolyte is called electrode potential. Factors affecting electrode potential. The factors which will affecting electrode potential. So we have three factors. One is nature of electrode, nature and concentration of ions in a solution. Third one is temperature. Nernst equation for Daniell cell. Zinc Daniell cell representation. Nernst equation E cell is equal to E naught cell minus 2.303 by 2.303 RT by 2F log Zn2 plus by C2 plus. When you take this entire value 2.303 RT by F, then that is equal to 0.0591. Then E cell is equal to E naught cell minus 0.0591 by 2 log Zn2 plus ion concentration by Cu2 plus ion concentration. Differences between EMF and cell potential. EMF is the potential difference between the two electrodes when no current is drawn through the cell. Cell potential means it is the difference between the electrode potential of two electrodes when the cell is under operation. That is the difference between EMF and cell potential. It is measured using potentiometer. It is measured using voltmeter. Electrochemical series, active series also. We will call it as active series. The series of arrangement of standard electrode is increasing order of standard reduction values. Next concept in electrochemistry, relation between standard cell potential gives standard free energy change delta Z naught. That is delta Z naught is equal to minus NF E naught cell. Delta Z naught is standard free energy change. F is Faraday, 96,500. That is 1 Faraday is equal to 96,500. N is number of electrons in a redox reaction. E naught is standard cell potential. E naught cell is greater than 0 means positive. Delta Z less than 0 negative, then the reaction is spontaneous. When E naught cell is less than 0 negative, then delta Z naught greater than 0 positive, the reaction is non-spontaneous. When E naught cell is equal to 0, delta Z naught also equal to 0, then the reaction is in equilibrium. Next, take a relation between Gibbs standard free energy change and equilibrium constant. That is delta Z naught is equal to 2.303 RT log Kc. Kc is equilibrium constant. R is 8.314. Relation between standard cell potential and equilibrium constant. That is E naught cell is equal to 0.059 by N log Kc. Here N is equal to number of electrons involved. Summary. If Kc is greater than 1, delta Z less than 0 negative, then the reaction is spontaneous. Kc is less than 1, delta Z greater than 0, non-spontaneous. Kc is equal to 1, delta Z is 0 at equilibrium. Primary batteries. Now about batteries, electrochemical cells. Primary battery, one which becomes dead over a period of time and cannot be recharged. Example, dry cell, Leclanche cell, mercury cell. Dry cell, anode, zinc, cathode, graphite rod which is surrounded by MnO2 and powder of carbon. Electrolyte, moist paste of ZnCl2 and NH4Cl. Reactions, at anode, Zn gives rise to Zn2 plus and 2 electrons. At cathode, MnO2 plus 2 NH4 plus and 2 electrons gives rise to MnOOH plus NH3. Next, mercury cell. mercury cell. Anode is zinc amalgam ZnHg. Cathode is mercury oxide and carbon. Electrolyte is potassium hydroxide and zinc. Reactions at anode, zinc amalgam in the presence of OH minus base undergoes oxidation, forms ZnOH2, lose electrons. At cathode, HgO takes 2 electrons in the presence of water, forms Hg. The cell potential of mercury cell remains constant throughout its life. It is suitable for low current devices like hearing aids. Secondary batteries, rechargeable batteries are called secondary batteries. Lead storage cells, nickel cadmium cells. Lead storage battery. Anode in lead storage battery is lead. Cathode is lead dioxide. Electrolyte is 38% of sulfuric acid. Important. Reactions. At anode, lead undergoes oxidation, forms lead sulfate. Cathode, lead dioxide forms lead sulfate, undergoes reduction. Yeah, electrochemistry over. Next, unit 3, chemical kinetics. Rate of chemical reaction. The change in molar concentration of reactant or product in unit time is known as rate of chemical reaction. Unit for rate of reaction is moles per liter per second. The unit for the rate of gaseous reaction atmospheric per second. Average rate, the rate of reaction measured over a long interval of time. Instantaneous rate, the change in molar concentration of either reactant or product is extremely small interval of time, that is instant rate. Factors affecting the rate of reaction. Molar concentration of the reactant, one factor. Temperature is second factor. Catalyst, third. Intensity of light. Based on these four, the rate will depend. Rate law of Moss action, states that at constant temperature, the rate of a reaction is directly proportional to product of molar concentration of reactants, and each concentration term is raised to suitable powers which may or may not be same as the stoichiometric coefficient of reactants in balanced chemical equation. Rate expression or rate equation. It is an equation that relates the rate of the reaction and molar concentration of reactant. Order of reaction. The sum of power concentration of the reactants in experimental determination of rate equation. Next point, molecularity. The number of reacting species taking part in an elementary reaction or in rate determining step of a complex reaction which collides simultaneously to bring about a chemical reaction. Examples for order of molecularity: decomposition of ammonium nitrite, molecularity 1; decomposition of HI, molecularity 2; decomposition of combination of NO2 and O2, formation of NO2, molecularity 3. Units rate constant, order of reaction and unit rate constant. For nth order, moles per mole to the power 1 minus n, L to the power n minus 1 per second. Here n is order, number, nth order. For 0 order, n becomes 0, then unit is moles per liter per second. For first order, per second; second order, liter per mole per second. Differences between order and molecularity. Order is the sum of power concentration of the reactants in rate law. Molecularity means it is the number of molecules of reactants taking part in an elementary reaction in a rate determining step of complex reaction. It is an experimental value. It is a theoretical value. Order of reaction is experimental value. Molecularity is theoretical value. Order can be 0 or fraction, but molecularity cannot be 0 or non-integer. Order is applicable to elementary as well as complex reaction. Molecularity applicable only for elementary reaction. Okay, one by one we'll discuss. Zero order reaction. The reaction in which rate of reaction is independent of concentration of the all the reactants. Example, decomposition of NH3 on platinum surface is an example for 0. Means the rate of reaction does not depends upon concentration of NH3. Decomposition of HA on gold surface. Zero order reaction, the rate of reaction is equal to the rate constant of the reaction. Why? Because rate is equal to K into R to the power of 0. R to the power of 0, 1. Then rate is equal to K into 1. Then rate is equal to K. Units of rate is same as that of rate constant. Graph R is equal to minus kt, or consider it is a y is equal to mx plus c straight line equation. We plot a graph R versus t time, straight line with a slope m, that is minus k, and intercept c r naught. So graphical representation: on x axis time, on y axis concentration of reactant. Then we will get a straight line, negative slope. Intercept is r naught, slope is minus k. First order, the reaction in which rate of reaction is directly proportional to first power of molar concentration of reactants. Example, hydrogenation of ethene. C2H4 ethene, add hydrogen, forms ethene. All natural and artificial radioactive disintegrations. Example for first order. Decomposition of N2O and N2O5. Thermal decomposition of hydrogen peroxide. First order reactions. Graph for first order ln minus kt plus ln r naught. Y is equal to mx plus c, straight line. Plot a graph ln r versus time, straight line with a slope minus k, intercept ln r naught. Log r naught by r is equal to kt, 2.3 is also y is equal to mx plus c, straight line equation, but with positive slope. When you take log, when you take ln, negative slope. When you take log, we will get positive slope. Then slope k by 2.3, here slope is minus k. That is the difference. Half-life of reaction. The time at which the concentration of reactant to reduce to half of its initial concentration. Derivation of half-life for zero order reaction, or show that half-life for zero order reaction is directly proportional to initial concentration of reactant. T is equal to Tf when R is equal to R naught by 2. We know that K is equal to R naught minus R by T for zero order reaction. When you consider R is equal to R naught by 2, T is equal to Tf, then we'll get this expression. Tf is equal to R naught by 2K. Half-life is directly proportional to initial concentration of the reactant. It is for zero order reaction. Half-life of zero order reaction is directly proportional to initial concentration of reactant. Derivation of half-life for first order reaction. Show that half-life of a first order reaction is independent of initial concentration. Take a rate equation for first order reaction. Here R is equal to R naught by 2, T is equal to T off. When you substitute these two in this expression, we'll get T off is equal to 2.303 into log 2 by K. Here log 2 value 0.3010. When you substitute that, multiply these two values, we'll get 0.693. That's why T of half-life of first order reaction is equal to 0.693 by K. Half-life of the first order reaction is independent of the initial concentration. Pseudo first order reaction. Next one, pseudo first order reaction. A reaction of higher order can be converted into first order by altering the reaction conditions, is called pseudo first order reaction. Examples: inversion of cane sugar. Sucrose undergoes hydrolysis, gives glucose and fructose. It is an example for pseudo first order. It seems to be higher, but it follows first order reaction. Temperature depends of the rate of reaction. Rate of chemical reaction increases with increase in temperature. For every 10 Kelvin, 10 degrees Celsius rise in temperature, rate of reaction gets doubled. The ratio of rate constant for a reaction at T plus 10 degrees Celsius to the rate constant at T degrees Celsius is called temperature coefficient. T plus 10 by T degrees Celsius is known as temperature coefficient. The minimum energy that the reactant molecule should possess to form products upon effective collision is called threshold energy. Energy required to form activated complex is called activation energy. The collisions between molecules with the sufficient kinetic energy and proper orientation is called effective collisions. Arrhenius equation. The equation gives the relationship between rate constant, temperature and Arrhenius activation energy. K is equal to A into e to the power of minus EA by RT. K is rate constant of the reaction, A is Arrhenius factor, EA is activation energy in joules, T is temperature in kelvins. Ln, take a ln for this equation, ln minus EA by RT plus ln A will get, it is also y is equal to mx plus C formula, slope is minus EA by R, intercept is ln A, slope with a negative sign. Calculations of activation energy at two different temperatures. Formula log K2 by K1 EA by 2.303 T2 minus T1 by T1 into T2. Using this equation we can solve for EA. R is equal to 8.314. Catalyst, a substance which alters the rate of reaction without undergoing any chemical change during the reaction. Effect of catalyst on rate of reaction. It is important for PU. In the reaction, catalyst provides an alternate path with lower activation energy for the reaction. Hence, the rate of reaction increases in the presence of catalyst. So, here this is first one without catalyst, here it is with catalyst. So, activation energy decreases. Important point, catalyst decreases the activation energy of reaction. Catalyst alters the activation energy, threshold energy, rate of reaction, rate constant and path of the reaction. Catalyst does not alter the Gibbs free energy, delta S, delta H, equilibrium constant, energy of reactants and products. In case of reversible reaction, the catalyst lowers the activation energy of both the forward and backward reaction to the same extent and helps in attaining the equilibrium quickly. It catalyzes the spontaneous reactions but does not catalyze non-spontaneous reactions. Collision theory of chemical reaction. Next point. Conditions or criteria for effective collisions between the reactants molecules. Proper orientation, sufficient kinetic energy, that is threshold energy. Collision frequency. Collision frequency, the number of collisions per second per unit volume of the reaction mixture. For biomolecular elementary reaction, A plus B gives rise to product. Rate of reaction can be expressed as rate is equal to P into ZAB e to the power of EA minus EA by RT. P is proper orientation, Z is collision frequency, R is universal gas constant, T is absolute temperature, EA is activation energy. That's it. Next, fourth chapter, D and F block elements. D series. D block elements are classified into 4 series: D, 3D, 4D, 5D, and 6D series. About 3D series, general electronic configuration: argon 3D 1 to 10, 4s 1 to 2. Exceptional electronic configuration for chromium, atomic number 24, argon 4s1 3D 5. Due to extra stability of off-filled D5 configuration. Copper, atomic number 29, electronic configuration argon 4s1 3D10 due to extra stability of completely filled D10 configuration. Zinc, cadmium and mercury are non-transition elements due to completely filled D10 electronic configuration. Variable oxidation state. All transition elements show variable oxidation state because of small energy difference between N-1D and Ns orbitals. The electrons present in both N-1D and Ns orbitals are involved in bond formation. The most common oxidation state of 3D series is +2. Scandium do not show variable oxidation state. 3D series manganese Mn shows maximum oxidation state, that is +7. Example for amphoteric oxide Cr2O7 and V2O5. Formation of colored ions. The color of the transition metal compounds due to presence of unpaired electrons which undergoes DD transition by absorbing the energy from visible region. In the presence of light, the degenerated d orbitals are split up into two sets of orbitals T2z and Az having different energies is called crystal field splitting. Magnetic property. Magnetic property of transition metals ions is mainly due to presence of unpaired electrons. Spin only formula to calculate the magnetic momentum is mu is equal to under root of n into n plus 2 Bohr magneton. Here the n is number of unpaired electrons. Catalytic property. Next, property of transition elements, that is catalytic property. Transition metals and their compounds used as catalyst because they have tendency to show variable oxidation state, tendency to lowering the activation energy by weakening the bonds, tendency to form reactive intermediates with reactants. Next property, formation of complex coordination compounds. Transition metals forms complexes mainly due to presence of weakened d orbitals, higher polarizing power, high charge and small size, high charge density. Next, interstitial compounds. The compounds which are formed when small atoms like hydrogen, boron, nitrogen and carbons are trapped inside the crystal lattice of metals. The example, titanium carbide TiC. Transition metals forms interstitial compounds because presence of space between metal atoms in their crystal lattice. Tendency to show variable oxidation state. Characteristics of interstitial compounds. The, they have high melting point compared to pure metals. They retain their metallic conductivity. They are chemically inert. They are hard and denser. Next, alloy formation. An alloy is a homogeneous solid solution in which atoms of one metal distributed randomly among the atoms of other. Transition metals forms alloys among themselves because they have similar atomic radii. Allied transition metals with non-transition metals are brass, copper and zinc, bronze, copper and tin. Disproportionation of oxidation state. The oxidation state is said to be undergo disproportionation when it is less stable relative to other oxidation state. One is lower, one is higher. Example, copper plus 1 undergoes disproportionation from Cu and Cu2 plus. Variation of atomic and ionic radii. In the beginning, scandium to chromium atomic and ionic size decreases because of increase in effective nuclear charge. From manganese to copper, atomic and ionic size almost constant because increase in screening effect balanced by increased electroeffective nuclear charge. Towards end, atomic and ionic size increases because of interelectronic repulsions. Electron expands, hence size increases. Next one, melting point, boiling point and enthalpy of atomization. The melting and boiling points or transition metals are maximum at middle of each series. Reason, due to the presence of more number of unpaired electrons in the middle of each series, metallic bonding between the atoms is very strong. Therefore, they have high melting and boiling point. Enthalpy of atomization maximum in middle of the each transition series due to the more number of unpaired electrons in the middle each series of interatomic interaction is longer. Therefore, enthalpy of atomization is maximum in the middle of each transition series. Enthalpy of atomization is more in 4D and 5D series than 3D. Reason, this is due to the strong metal-metallic bond 4D and 5D series elements than 3D series elements. Action of heat on KMnO4. KMnO4 decomposed at 513 kelvins temperature gives potassium manganate, manganese dioxide and oxygen. When KMnO4 heated at 513 kelvins forms potassium manganate, manganese dioxide and oxygen. The lanthanides 4F black elements and actinide 5F black elements. The lanthanides are those elements in which differentiating electron enters the antipenultimate 4F subshell. General electronic configuration of lanthanides: xenon 4F 1 to 14 5D 0 to 1 6s2. Actinides are those elements in which differentiating electron enters the antipenultimate 5F subshell. General electronic configuration of actinide is radon 5F 1 to 14 60 0 to 1 7s2. All actinides are radioactive elements. Radioactive lanthanide is promethenium Pm. An element with atomic number 100 is fermium, the symbol Fm. Cerium Ca atomic number 58, This is electronic configuration. Gadolinium Zd64 electronic configuration. Zd plus 3 electronic configuration. Xenon 4f7. Oxidation state. The common oxidation state of lanthanide and actinide is plus 3. The stable oxidation state of cerium in aqueous solution is plus 3. Actinides show more oxidation state compared to lanthanide due to comparable energies between 5F, 6D and 7S levels. Cerium does not exist plus 4 oxidation state in aqueous solution. Reason: because cerium plus 4 is strong oxidizing agent, it can easily reduce to C3 plus. Due to this, lanthanide contraction. The gradual decrease in size of lanthanides with increasing atomic number. Cause of lanthanide contraction: poor shielding of inner 4f electrons. Consequences of lanthanide contractions: radii of the elements belonging to the same group of second and third transition series is same. Example, zirconium and hafnium has same size. Neodymium, thallium has same size. Separation of lanthanide ions from their mixture becomes difficult. Actinide contraction. The gradual decrease in the size of actinides with increase in atomic number. Cause for actinide contraction: poor shielding of 5f electrons. Actinide contraction is greater from one element to another. The lanthanide contraction due to poor shielding of 5f electrons in actinides than 4f electrons in lanthanides. 5f electrons in actinides, 4f electrons in lanthanides. Actinides are more reactive than lanthanides because actinides 5f electron will be more effectively shielded from the nuclear charge than 4f electrons of the corresponding lanthanide. Hence, the outer 5f electron less firmly held and are available for bonding. Chemistry of actinides more complicated compared to lanthanide because actinides are radioactive nature. Actinides have greater range of oxidation state compared to lanthanide. That's it, students. It is about D and F block elements. Last one concept is there, that is difference between lanthanides and actinides. It is important, very very important. Lanthanides are electrons enters into 4f, here 5f. Maximum oxidation state of lanthanides plus 4, actinides plus 7. 4f electrons have greater shielding effect, here 5f effect. Lanthanide contraction is lesser, actinide contraction is greater. Except promethenium, all are non-radioactive. Here actinides all are radioactive. That's it about D and F block elements. Next, coordination compounds. First important in this chapter postulates assumption of Werner's theory of coordination compounds. In coordination compounds, the central metal atom possesses two types of valencies: primary valency, secondary valency. Primary valency is ionizable, variable, and corresponds to oxidation state of central metal atom. Secondary valency is non-ionizable, non-variable, and corresponds to coordination number of central metal atom. Primary valency is satisfied by negative ions. Secondary valence satisfied by negative or neutral molecules. Primary valency is non-directional, but here secondary valency is directional. Difference between double salt and complex salt of coordination compounds. Double salt means it loses its identity in solution, but complex salt, it retains its identity in solution. It does not contain coordination bonds. In double salt, no coordination bond, but in complex, there is a covalent bond. It is stable in solid state. Complex is stable in solid state and in aqueous state, but double salt is unstable in aqueous state. Now complex compounds are classified in two types, homoleptic, heteroleptic complexes. Complexes in which central metal ion attach to only one kind of ligand called homoleptic complexes. Example NiCO taken 4 times. The complex in which central metal ion attach to more than one kind of ligand called heteroleptic complexes. Example PtCl2NH3 taken PtCl2 NH3 taken twice. Ambidentate ligand, a monodentate ligand which has two different donor atoms and either of two ligate in the complex. The coordination compound containing ambidentate ligand shows the linkage isomerism Cn minus NO2 minus SCN minus. Chelating agent. Chelating agent means a bidentate or polydentate ligand which can attach to central metal ion through two or more donor atom is called chelating agent. Bidentate or polydentate ligand which can attach to central metal ion through two or more donor atom is called chelating agent. Example ADTA. Denticity of ligand. The number of ligating group in a ligand is called denticity of the ligand. Coordination number of central metal ion. The number of coordinate bonds between the ligand and central metal atom or ion in complex is called as a coordination number. Spectrochemical series. The series of ligands arranged in increasing order of their field strength to split the d orbital is called spectrochemical series. Ligands, monodentate ligands, the ligand which can donate only one lone pair of electrons to the central metal atom. Example H2O NH3CO, neutral ligands, Cn minus, Cl minus, Br minus, negatively charged ligands. Di or bidentate ligands, the ligands which can donate two pair of electrons to the central metal ion. Example ethylene diamine, that is neutral, oxalate ion, negatively charged ligand. Hexadentate ligand, the ligand which can donate 6 pair of electrons to the central metal ion. Example ADTA. Structural isomerism in complexes. Ionization isomerism, linkage isomerism, hydrate or solvate isomerism, coordinate isomerism. Ionization isomerism means isomer which gives different ions on ionization in water called ionization isomers. And phenomenon is known as ionization isomerism. Example platinum NH3 taken 4 times, Cl2 square bracket close, Br2 outside the square bracket, and PtNH3 taken 4 times, Br2 square bracket close and Cl2 outside the square bracket. Linkage isomerism. Isomers different in the mode of attachment of monodentate ligand, ambidentate ligand with central metal ion called linkage isomerism, and phenomenon is called as linkage isomerism. Example NO2, these two. Linkage arises when ambidentate ligands such as NO2 minus, Cn minus, SCN minus present in coordination compounds. Other than this, only with this the compound will show linkage isomerism. Hydrate or solvent isomerism. Isomers which differ in the number of water molecules in coordination sphere called hydrate isomers, and phenomenon is called hydrate isomerism. Example Cr H2O taken 5 times, Cl inside the square bracket and Cl2 H2O outside the square bracket. Cr H2O taken 4 times, Cl2 Cl and 2 H2O outside the square bracket. Differ in number of water molecules in and outside the square bracket, known as hydrated isomerism. Coordinate isomerism. The isomerism arises due to the interchange of ligands in the coordination sphere of cationic and anionic part of complex. Examples these two. Cis and trans isomer of PTCl. When similar groups present adjacent to each other, cis, opposite to each other, trans. Here cis and trans isomerism in CONH3 taken 4 times Cl2, that is Ma3B Ma4B2. When similar groups are adjacent to each other with 90 degrees bond angle, then it is cis form. When similar groups are opposite to each other with 180 degrees, that is trans form. Cis and trans isomerism in FeNH3 taken twice Cl4. Here also same, similar groups adjacent to each other cis, similar groups are opposite to each other trans. Cis and trans isomerism COEN taken twice Cl2. Similar groups adjacent cis, opposite trans. Another one facial and meridial isomerism, it is in Ma3B3 type molecule. So when similar groups are adjacent, facial, not adjacent, 3 are not in adjacent to each other, then it is meridial. Optical isomerism, dextro and levo. For platinum CON taken thrice, it is dextro and levo, and here also dextro and levo. Crystal field splitting degenerated d orbitals in octahedral complex. D orbitals 5 dxy, dxz, dyz, dx square, y square and z square. These 5 orbitals takes energy, will go to the higher energy state, and when ligand will approaches this ligand central metal atom, split into two set EZ and T2G. T2G has 3 dxy, dyz, dxz, and EZ has 2 dx square, y square and dz square. It is energy barrier. Difference in energy between these two delta O. Energy of EZ increased by plus 3 by 5 and energy of T2G decreased by minus 2 by 5 delta O. Crystal field splitting of degenerated d orbitals in tetrahedral. D orbital split into two set, one is T2 and E. So E is lower energy, T2 is higher energy. T2 has dxy, yz, xz, opposite to octahedral. Importance and applications of coordination compounds. Cisplatin is used in treatment of cancer. Hemoglobin is Fe2 plus complex present in blood, responsible for a transport of oxygen and carbon dioxide throughout the body. The ligand EDTA 4- used to determine the hardness of water. Na2 plus ion is estimated gravimetrically by complexing with DMG, dimethyl glyoxime. Rhodium complex is Wilkinson catalyst used for selective hydrogenation of alkene. Extraction of gold and silver through the formation of cyanide complex. Mond's process, impure Ni is purified by converting into NiCO taken 4 times complex. These are all the application and importance of coordination compounds. Metal carbonyls. Metal carbonyls are the organometallic complex compounds in which ligand is carbon monoxide. Bonding in metal carbonyls. In metal carbonyls, the metal carbon has both sigma and pi bond character. MC sigma bond is formed by donation of pair of electrons of carbonyl carbon to the vacant orbital of the metal. MC pi bond is formed by donation of pair of electrons from the filled d orbitals of metal to vacant antibonding pi star orbital of carbonyl group. The effect of sigma bond formation strengthens the pi bond and vice versa. This is called synergic effect. Important. Synergic effect. Next, sixth chapter, haloalkane and haloarenes. Few important points only will discuss. Finkelstein reaction, alkyl chloride or alkyl bromide on heating with sodium iodide in dry acetone gives alkyl iodide. This reaction is called Finkelstein reaction. General reaction, Rx plus NaI in dry acetone gives Ri plus Nx, where X is chlorine or bromine. Schwarz reaction. Schwarz reaction means Alkyl chloride or alkyl bromide on heating with AgF COF3Hg2F2 or SbF3 gives alkyl fluoride. This reaction is called Schwarz reaction. Example, CH3Cl methyl chloride reacts with AgF gives CH3F methyl fluoride and AgCl. Next named reaction, Wood's reaction. When alkyl halides heated with sodium metal in the presence of dry ether gives higher alkanes. This reaction is called Wood's reaction. Alkyl halide reacts with sodium in dry ether gives higher alkanes, and it is example. Wood's fatigue reaction. Here, when mixture of aryl halide and alkyl halide treated with sodium metal in dry ether gives alkyl arenes. This reaction is called Wood's fatigue reaction. Examples, general equation, and it is example. Fatigue reaction. Aryl halide reacts with sodium metal in dry ether to give diphenyls or biphenyl. This reaction is called fatigue reaction. See here haloarine, here also haloarine. Two haloarines react with 2 moles of sodium forms diphenyl or biphenyl. Example, bromobenzene reacts with sodium metal forms diphenyl. Dehydrohalogenation. Statement for this. Alkyl halide containing beta hydrogen atom undergoes elimination reaction in presence of alcoholic potassium hydroxide gives alkene. This reaction is called dehydrohalogenation. During dehydrohalogenation, hydrogen is removed from the beta carbon atom in alkyl halide. Hence, the reaction is called beta elimination reaction. Reagent used for dehydrohalogenation is alcoholic potassium hydroxide, known as alcoholic potash. CET&PUC rule. In dehydrohalogenation reaction, preferred product is alkene, which has greater number of alkyl group attached to the double bonded carbon atom. When you take 2-bromopentane treated with alcoholic KOH gives pent2-ene as a major, pent1-ene as a minor product. Haloarenes or aryl halides are extremely less reactive towards nucleophilic substitution reaction due to following reasons. First one, in haloarenes, due to resonance, CX bond acquires double bond character. Hence, bond strength increases. So, difficult to break down CX bond. Due to instability of phenyl carbocation formed after self ionization, and therefore SN1 mechanism ruled out. Benzene ring is electron rich, so nucleophile cannot attack it easily due to repulsions. Nucleophilic substitution reaction of alkyl halide. Rx reacts with KCN gives RCN. Rx reacts with AgNO2 gives RNO2. Rx reacts with AgCN gives RNC. Rx reacts with KNO2 gives RONO. Conversion of chlorobenzene to phenol. Chlorobenzene reacts with sodium hydroxide at 623 Kelvin's temperature and 300 atmospheric pressure, followed by acidification gives phenol. This is the reaction. Chiral carbon atom and asymmetric carbon atom, chirality center, stereo center. A carbon atom bonded to 4 different atoms or groups is called chiral carbon atom. Chiral molecule, the molecules which contain non-superimposable on their mirror images are called chiral molecules. Achiral molecules means the molecules which are superimposable on their mirror images called achiral molecules. Chirality, the property of molecule which are non-superimposable on their mirror image. Condition for molecule to said to be chiral molecule, molecule should contain chiral carbon, optically active compounds. The compounds which rotates the plane polarized light when it is passed through its solution are called optically active compounds. Optically activity means the property of a compound to rotate plane polarized light when it is passed through it Solution is called optical activity. Condition for optical activity. Compound should not contain plane of symmetry. Racemic mixture or racemic modification. Equimolar mixture of dextro and levo isomers of same compound is called racemic mixture. Racemic mixture is optically inactive because optical rotation produced by dextro isomer is cancelled with optical rotation produced by L isomer. Racemization, the process of conversion of enantiomer into racemic mixture, is known as racemization. Next, electrophilic substitution reaction. Electrophilic substitution reaction, ESR. First one, halogenation. Chlorobenzene reacts with chlorine in the presence of FeCl3 gives 1, 2 dichlorobenzene and 1, 4 dichlorobenzene as a major. Nitration. When chlorobenzene reacts with HNO3 gives orthonitrochlorobenzene minor and paranitrochlorobenzene as major. Sulfonation. When chlorobenzene reacts with concentrated sulfuric acid gives orthochlorobenzene sulfonic acid as a minor product and parachlorobenzene sulfonic acid as major product. Friedel-Crafts alkylation. When chlorobenzene reacts with CH3Cl in the presence of anhydrous AlCl3 gives orthochlorotoluene, parachlorotoluene. Here parachlorotoluene is major product. Friedel-Crafts acylation of chlorobenzene. When chlorobenzene reacts with acetyl chloride in the presence of anhydrous AlCl3 gives 2-chloroacetophenone, 4-chloroacetophenone. Out of these two, 4-chloroacetophenone is major. Freons. Chlorofluorocarbons of methane and ethane are called freons. When chloroform exposed to sunlight and air, it slowly undergoes oxidation, forming poisonous gas phosgene carbonyl chloride. Hence, chloroform stored in dark colored bottles which are completely filled with air gap, DDT, P, P dash dichloro-diphenyl trichloroethane. It is the first chlorinated organic insecticide. Drawbacks of DDT: it non-biodegradable, chemically stable and fat soluble. Structure of DDT. Yeah. Next, seventh chapter, alcohol, phenols and ethers. So after haloalkanes, the next one is alcohol, phenols and ethers. Distinguish are identification of primary, secondary and tertiary alcohols by Lucas test. Lucas reagent. Lucas reagent means mixture of anhydrous zinc chloride and concentrated hydrochloric acid HCl is known as Lucas reagent. Test. Alcohol plus concentrated HCl and anhydrous ZnCl2 in a test tube. Observation: turbidity appears immediately, then inference is tertiary alcohol. Turbidity appears after 5 minutes, indicate presence of secondary alcohol. Turbidity appears only on heating, then it indicates primary alcohol. Coal-base reaction, conversion of phenol to salicylic acid. When sodium phenate heated with carbon dioxide followed by acidification gives salicylic acid. This reaction is called coal-base reaction. This is a reaction. Phenol reacts with sodium hydroxide gives sodium phenate. Sodium phenate on heated with carbon dioxide and HCl followed by acidification gives salicylic acid. Next named reaction, Reimer-Tiemann reaction. For this reaction, when phenol is treated with chloroform in the presence of sodium hydroxide followed by hydrolysis gives salicylaldehyde. Reaction: phenol treated with NaOH in the presence of chloroform. Treated with chloroform in the presence of NaOH gives an intermediate and again converts to sodium salt of benzaldehyde followed by acidification gives salicylaldehyde. Next named reaction, Williamson synthesis. When sodium alkoxide is heated with alkyl halide, then ether is formed. This reaction is called Williamson's ether synthesis. This reaction takes place by SN1 mechanism. See the reaction, general equation, sodium alkoxide treated with alkyl halide gives ether. This reaction follows SN1 and it is example. Cumin process, preparation of phenol from cumin. IUPAC name of cumin is isopropyl benzene. When cumin undergoes oxidation in the presence of air, forms cumin hydrogen peroxide. Cumin hydrogen peroxide followed by hydrolysis gives phenol and acetone. Conversion of salicylic acid to aspirin. Salicylic acid is treated with acetic anhydride in presence of concentrated sulfuric acid gives aspirin. Reaction is called acetylation. Salicylic acid when treated with acetic anhydride, presence of an acid forms aspirin. Acetyl salicylic acid another name. Hydroboration and oxidation reaction. Alkene reacts with diborane to give trialkyl borane, which on oxidation using hydrogen peroxide in alkali gives alcohol. This reaction is called hydroboration oxidation. Observe here carefully. Alkene, they took propene. So propene treated with B2H6 undergoes boration, forms triphenylborane followed by oxidation and hydrolysis gives alcohol. Nitration of phenol. Phenol reacts with concentrated nitric acid gives picric acid, that is 2,4,6 trinitrophenol. When phenol treated with dilute nitric acid at 298 kelvins gives mixture of ortho and para nitrophenols. Phenol treated with dilute, here concentrated means picric acid, dilute means ortho nitrophenol and para nitrophenol, two products. Bromination of phenol. When phenol treated with bromine, water gives 2,4,6 tribromophenol. When the phenol reacts with bromine in the presence of non-polar solvents like carbon disulfide or chloroform, gives ortho and para-bromophenol. Bromine water, tribromo. In the presence of Ca2, orthobromophenol and para-bromophenol as a measure. Reaction with zinc dust. When phenol is heated with zinc dust, gives benzene. Oxidation of phenol. Phenol undergoes oxidation by chromic acid, Cr2O3 or sodium dichromate, Na2Cr2O7 and H2SO4 gives benzoquinone. Preparation of methanol. When carbon monoxide CO reacts with hydrogen in the presence of ZnO and Cr2O3 at 200 to 300 atmospheric pressure and 573 to 673 kelvins temperature forms methanol. Preparation of ethanol from sucrose. This reaction is known as fermentation. Ethanol is prepared by fermentation of molasses by using enzyme present in yeast. When sucrose undergoes hydrolysis, invertage gives glucose and fructose. Glucose and fructose in the presence of zymase gives ethanol. Bromination of anisole. Anisole reacts with bromine in the presence of acetic acid gives orthobromoanisole and parabromoanisole. Nitration of anisole. Anisole reacts with mixture of HNO3 and H2SO4 gives orthonitroanisole and paranitroanisole. Friedel-Crafts alkylation of anisole. Anisole reacts with methyl chloride in the presence of anhydrous AlCl3 gives 2-methoxytoluene and 4-methoxytoluene. Friedel-Crafts acylation of anisole. Anisole reacts with acetyl chloride in the presence of anhydrous AlCl3 gives 2-methoxyacetophenone and 4-methoxyacetophenone. Here it is major and it is minor. Esterification. Esterification means alcohol reacts with carboxylic acid in the presence of concentrated sulfuric acid or dry HCl gives ester. This reaction is known as esterification, and this is the reaction for that. Effect of substitution on acidity of phenols. Electron donating group like methyl group decreases the acidity of phenols by decreasing the stability of phenoxide ion due to plus I effect. Electron withdrawing group like NO2 group increases the acidity of phenols by increasing stability of phenoxide ion due to minus effect or and minus R effect. Dehydrogenation of alcohol. Copper used as a dehydrating agent. Primary alcohol undergoes dehydration gives aldehydes. Secondary alcohols on dehydration gives ketone. Tertiary alcohols do not undergo hydrogenation. Instead of they undergoes hydration gives alkene. Denaturation of alcohol. The commercial alcohol is made of unfit for drinking by mixing it some copper sulfate to give it color and pyridine, foul smelling liquid. This process is called denaturation of denaturation of alcohol. Structure of some phenols: orthocresol, metacresol, paracresol, dihydric phenol, catechol, resorcinol, quinol or hydroquinone. Reasoning type questions. Phenol or acidic? Reason: because phenols dissociate partially to give H plus ion and phenoxide ion in which stabilized by resonance. Alcohols are weaker acidic than phenol. Reason: because in alcohol the alkoxide ion do not undergoes resonance stabilization as like phenoxide. The COH bond angle in alcohol is slightly less than tetrahedral angle 109.28 due to the repulsion between the lone pair of electrons on oxygen atom. COH bond angle in phenyl is slightly higher than alcohol because lone pair electron involves in the resonance, hence repulsion between the lone pair electron decrease, bond angle increase. The CO bond length in phenol is less than that of alcohol. Reason: because of lone pair of electrons in phenol involves in resonance, hence CO bond acquires double bond character. So CO bond length decreases in phenol. The bond angle in ether is higher than the tetrahedral angle 109.28 due to steric repulsion between bulky alkyl group. Bond angle in ether higher than tetrahedral angle. Some important MCQs concept. Diazonium salt hydrolyzed by warming with water or with diluted acid gives phenol. Primary alcohol on oxidation using pyridinium chlorobenzene PCCrCrO3 gives aldehyde. Secondary alcohol on oxidation using CrO3 gives ketone. When carboxylic acids are reduced by LiLH4, gives primary alcohols are formed. Reactions are given. Next unit, carbonyl compound. Hybridization of carbonyl carbon atom is sp2. Rosenmund reduction, first named reaction in this chapter. Acid chloride or acyl chloride reacts with hydrogen in the presence of palladium as a catalyst on barium sulfate gives aldehyde. This reaction is known as Rosenmund reduction. Benzaldehyde it is hydrogen, barium sulfate, palladium as a catalyst. Product is benzaldehyde. Stefan's reduction. Nitriles on reduction with stannous chloride in the presence of concentrated HCl gives imine hydrochloride, which on hydrolysis gives analdehyde. This reaction is called Stefan's reduction. General equation and example. Ettard reaction. Toluene undergoes oxidation with chromyl chloride to form a chromium complex which is on hydrolysis gives benzaldehyde. This reaction is called Itard reaction. This is a reaction. Oxidizing agent in Itard reaction is chromyl chloride. Formula CrO2 Cl2. Next, Gattermann-Koch reaction. Benzene is treated with carbon monoxide and HCl in the presence of anhydrous aluminum chloride or cuprous chloride gives benzaldehyde. This reaction is called Gattermann-Koch reaction. Equation they given. Clemmensen reduction. Reduction of CO group of aldehyde or ketone to CH2 using ZnHz and concentrated HCl is called Clemmensen reduction. See, observe carefully. Here C double bond O converted to CH2. Reagent used in this reaction, zinc amalgam and concentrated HCl. Next one, Wolff-Kishner reduction. Wolff-Kishner reduction. The aldehyde and ketones reacts with hydrazine followed by treating with KOH in ethylene glycol gives hydrocarbons. This reaction is called Wolff-Kishner reduction. Observe here C double bond O connected to CH2. Kenizaros reaction. How formaldehyde or benzaldehyde does not react with concentrated NaOH or KOH. Kenizaros reaction. Aldehydes which do not contain alpha hydrogen atom or reacts with concentrated alkali gives an alcohol and salt of carboxylic acid. This reaction is called Kenizaros reaction. Examples: formaldehyde, benzaldehyde undergoes Kenizaros reaction. Aldol condensation. Aldehydes and ketones containing alpha hydrogen undergoes self condensation in the presence of dilute alkali to form beta hydroxyaldehyde or beta hydroxyketone, that is ketol. Beta hydroxyaldehyde is aldol. What is beta hydroxyaldehyde? That is aldol. Beta hydroxyketone is ketol. ఇంకా ఒక 2 చాప్టర్లు ఉన్నాయమ్మా. ఏమి నువ్వు పొనుకొనక పోయి చేయనా లేదంటే aldol condensation. Aldehydes and ketones containing alpha hydrogen undergo self condensation in the presence of dilute alkali to form beta hydroxyaldehyde known as aldol or beta hydroxyketone known as ketone respectively, which is on heating forms alpha beta unsaturated aldehydes or ketones with elimination of water. This reaction is called aldol condensation reaction. For that, cross aldol condensation or mixed aldol condensation. When aldol condensation is carried out between two different aldehydes or different ketones or between aldehyde and ketone, it is called cross aldol or mixed aldol condensation. One is benzaldehyde, another one is acetophenone. It gives benzol acetophenone. Hoffmann reaction. When aldehyde and ketone having at least one methyl group linked to carbonyl carbon atom methyl ketone are oxidized by sodium hypohalite to sodium salt of carboxylic acid with one carbon atom less than that of the parent compound. The methyl group is converted to haloform CHX3. This reaction is known as haloform. General reaction, see here they given acetone treated with NaOI give sodium salt of carboxylic acid and iodoform. Acetaldehyde, ethanol is only one aldehyde which gives haloform reaction. Aldehydes are more reactive then ketones towards nucleophilic addition reaction because of the following reason. One is steric endurance, another one is electronic effect. Tollens reagent, ammonical silver nitrate solution. Filling solution means mixture of aqueous copper sulfate and alkaline sodium potassium tartarate. Methanol formaldehyde is a gas at room temperature. L. Volhard-Jelinski reaction, HVZ reaction. Carboxylic acid with alpha hydrogen atom reacts with chlorine or bromine in the presence of red phosphorus, gives alpha halo acid. This reaction is known as HVZ reaction. It is general reaction and example. Reaction with ammonia. When acetic acid reacts with ammonia, gives ammonium acetate. Upon heating gives acetamide. Benzoic acid gives ammonium benzoate, gives benzamide upon heating. Phthalic acid gives phthalimate. It is important. Reaction with PCl3, PCl5 and SOCl2. Carboxylic acid reacts with any one of these three, forms acid chloride. Remaining subproducts depends upon nature of reagents. Reduction of carboxylic acid. When carboxylic acid are reduced by a strong reducing agent like LiLH4 or diborane, primary alcohols are formed. Carboxylic acid treated with LiLH4, at that time product is alcohol. Esterification. Carboxylic acid reacts with alcohol in the presence of concentrate H2SO4 or dry HCl, gives ester. This reaction is called esterification. Examples for esterification, many examples they given. Note down this example, pause the video, take a screenshot and note down these examples. Formation of anhydrates. Carboxylic acid on heating with concentrated sulfuric acid or P2O5 gives corresponding anhydrate. See here, acetic acid upon heating with sulfuric acid or P2O5 gives acetic anhydrate by losing water molecule. Decarboxylation. The process of removal of carbon dioxide from sodium salt of carboxylic acid using dry soda lime is called carboxylation. Gives hydrocarbon. Sodium salt of carboxylic acid upon heating with sodium lime gives respective hydrocarbon. Here the mixture of NaOH and CaO is known as soda lime. The ratio must be in 3:1. Next one, organic compound containing nitrogen, we can call it as amines. Hoffman bromide degradation. Amides on heating with bromine in aqueous or ethanolic solution of NaOH gives primary amines. This reaction is called Hoffman bromide reaction. General equation, example 1 and 2. Here acetamide reacts with bromine, gives methylamine. Benzamide gives aniline. Hoffman bromide reaction is called degradation reaction because product obtained is contained one carbon atom is less than the amide. So it is called degradation reaction. Gabriel phthalimide synthesis. Potassium phthalimide on heating with alkyl halide followed by alkaline hydrolysis with alkaline hydrolysis gives primary amine. This reaction is called Gabriel phthalimide synthesis. When phthalimide reacts with potassium hydroxide gives potassium phthalimide, treated with alkyl halide gives N-alkyl phthalimide, followed by hydrolysis with NaOH gives sodium phthalate and primary amine as a main product. Reduction of nitro compounds. Nitro compounds on reduction using hydrogen in the presence of nickel, palladium or platinum as a catalyst are tin and concentrated HCl or Fe concentrated HCl or a lithium aluminum hydride gives primary amines. Nitro compounds reduced to primary amines. Ammonolysis. The process of cleavage of CX bond of alkyl halide by ammonia is called ammonolysis. When alkyl halide is treated with alcoholic ammonia in seal tube at 373 kelvins gives mixture of primary and secondary tertiary amines. Finally gives quaternary ammonium salt. See, primary amine with 1 mole of alkyl halide gives secondary amines. Next, tertiary amines and quaternary ammonium salt is final product. Carbylamine reaction. When aliphatic and aromatic primary amines are heated with chloroform and alcoholic potash gives isocyanate. This reaction is called carbylamine reaction. General equation example 1 and 2. Reaction with benzene sulfonyl chloride. Hinsberg reagent. Primary and secondary amines reacts with benzene sulfonyl chloride gives sulfonamide. This reaction is used to distinguish primary, secondary and tertiary amines. Primary amine reacts with benzene sulfonyl chloride to form N-ethyl benzene sulfonamide, which is soluble in alkali. Benzene sulfonyl chloride, ethylamine, N-ethyl benzene sulfonamide is product. Secondary amine reacts with benzene sulfonyl chloride to form N-N diphenyl sulfonamide, which is insoluble in alkali. Benzene sulfonyl chloride, N-N ethyl benzene sulfonamide with diethylamine. Tertiary amine does not react with benzene sulfonyl chloride due to absence of hydrogen and nitrogen atom. Diazotization. Aromatic primary amines reacts with nitrous acid gives benzene diazonium salt. This reaction is called diazotization. Aniline reacts with NaNO2 and HCl forms benzene diazonium chloride. This reaction is known as diazotization. Gattermann reaction. The process of introducing halogen atom into an aromatic ring by treating with diazonium salt with corresponding halogen acid in the presence of copper powder is called Gattermann reaction. Here, when benzene diazonium salts treated with HCl and copper chloride, copper or HBr in the presence of copper gives chlorobenzene or bromobenzene. Coupling reaction. Benzene diazonium chloride reacts with aromatic amines in weakly acidic medium or phenol in weakly basic medium to give azodies by coupling at ortho or para position of aniline or phenol. This reaction called coupling reaction. Benzene diazonium chloride reacts with phenol, forms para hydroxy azobenzene. It is orange dye. Benzene diazonium chloride with aniline gives para-amino-azobenzene, that is yellow dye. Electrophilic substitution reaction of aniline. Bromination. When aniline treated with bromine water gives 2,4,6 tribromoaniline. Nitration. Direct nitration aniline gives mixture of ortho 2%, meta 47%, para 51% of nitroaniline. Step to obtain para-bromoaniline. Procedure. Protecting amine group by acetylation with acetyl chloride. Bromination. Deprotonation of amine group by hydrolysis. First, aniline treated with acetic anhydride in pyridine gives acetanilide. That acetanilide undergoes bromination in the presence of acetic acid gives para-bromoacetanilide, followed by hydrolysis gives para-bromoaniline. Step 2, obtain para-nitroaniline. Protecting amine group by acetylation with acetyl chloride. The nitration then deprotect the amine group of bihydrolysis. Aniline first converted to acetanilide, it undergoes nitration in the presence of concentrated H10O3 and H2SO4 gives para-nitroacetanilide. Para-nitroaniline is the final product after hydrolysis. Boiling point. Amines having higher boiling point compared to corresponding hydrocarbons due to intermolecular hydrogen bonding in amines. The order of boiling point of isomeric amines in order primary greater than secondary than tertiary amines. Reason: the primary amines 2 hydrogen atoms in nitrogen involves in intermolecular hydrogen bonding. In secondary amines, the only one hydrogen atom or nitrogen involved in intermolecular hydrogen bonding. In tertiary amine, no intermolecular hydrogen bonding due to absence of hydrogen atom on nitrogen. Solubility. Aliphatic amines of lower molecular mass are soluble in water due to formation of hydrogen bond with water. Basic nature of amines. Amines are basic in nature due to the presence of lone pair of electrons on nitrogen atom. Hence they are behave as Lewis acid. Interpretation of basicity of alkylamine, ammonia and aniline. Alkylamines are more basic than ammonia due to plus psi effect of alkyl group, electron releasing group. Electron density on the nitrogen atom increases and hence easily available for donation. Methylamine is more basic than ammonia due to plus psi effect. Aniline are less basic than ammonia due to resonance effect of aniline. Variation basic strength of primary secondary amines. In gaseous phase, tertiary is greater than secondary than primary. Basic order, tertiary is greater than secondary and primary. Plus, due to plus. Steric endurance, primary is greater than secondary than tertiary. Based on hydration effect, basicity order is primary is greater than secondary than tertiary. Methyl substituted amines in aqueous solution, secondary is greater than primary than tertiary than ammonia. Ethyl substituted amine in aqueous medium, secondary is greater than tertiary than primary. Basicity is directly proportional to Kb, inversely proportional to pKb. Last chapter, biomolecules. Structures, how are the structure of beta D glucose? How are the structure of beta D glucose? Beta D means, sorry, alpha D and beta D. Alpha D means at first carbon OH downside, that's why it is alpha. At first carbon OH on top, that's why it is beta. Alpha D and beta D fructopyranose. At second carbon OH downside, that's why it is alpha. On top of the vertical line, that's why it is beta. How are the structure of maltose? Yeah, two monosaccharide unit, glucose unit, alpha D and alpha D. How are the structure of sucrose? One is glucose, another one is fructose. Glycosidic linkage between 1 and 2. How are the structure of lactose? One is beta D galactose, another one is beta D glucose unit. Here linkage is 1, 4. Reaction with HI, structural elucidation of glucose. Reaction with HI, glucose on heating with hydroiodic acid and red phosphorus undergoes reduction, gives N-hexane. This reaction indicates the presence of straight chain of 6 carbon atom in glucose, that is N-hexane. Next, reaction with hydroxylamine. When glucose reacts with hydroxylamine to give glucose oxime and reacts with HCN gives glucose cyanohydride. This reaction confirms the presence of carbonyl group, aldehyde or ketone in glucose. Reaction with bromine water. Glucose undergoes oxidation by mild oxidizing agent like bromine water gives gluconic acid. This reaction confirms that carbonyl group in glucose is an aldehyde. Next, reaction with acetic anhydride. When glucose reacts with acetic anhydride to give pentaacetyl glucose, this reaction, the presence of 5-OH group in glucose. This reaction indicates that presence of 5-OH group in glucose. Glucose undergoes oxidation by strong oxidizing agent like nitric acid gives succinic acid. This reaction confirms the presence of primary alcoholic group, that is saccharic acid. Reducing sugar and non-reducing sugar. The sugar which reduce the Tollens reagent and filling solution are called reducing sugar. Example: glucose, fructose, lactose, and maltose. The sugar which do not reduce the Tollens reagent and filling solution are called non-reducing sugar. Example: sucrose. Sucrose is non-reducing sugar. Why? In sucrose, carbonyl group involved in glycosidic linkage and hence it is not free to reduce Tollens reagent and failing solution. Storage of polysaccharide present in plant starch. Storage of polysaccharide plant in animals glycogen. Water soluble components of starch amylose. Water insoluble components of starch amylopectin. Predominant constituent of cell wall plant cell is cellulose. Example for aldohexose and dextrose is glucose. Example for ketohexose, fructose. Levorotatory sugar is fructose. Sugar present in milk, lactose. Invert sugar, sucrose. Monosaccharide present in starch, alpha glucose. Monosaccharide present in cellulose, beta D glucose. Animal starch, glycogen. Monosaccharide carbohydrates which contains hydrolyzed which cannot be hydrolyzed are called monosaccharides, glucose and fructose. Oligosaccharide, the carbohydrates which gives 2 to 10 monosaccharides units on hydrolysis are called oligosaccharides. Example: maltose and sucrose. Maltose on hydrolysis gives 2 molecules of glucose. Sucrose on hydrolysis gives glucose and fructose. Lactose on hydrolysis gives glucose and galactose. Polysaccharide, the carbohydrates which gives many monosaccharide units on hydrolysis called polysaccharides. Example: starch and glycogen. Difference between amylose and amylopectin. Amylose is water soluble component. Amylopectin is water insoluble component. Amylose is linear chain polymer. Amylopectin is branched chain polymer. Next, protein in biomolecules. Denaturation of protein. The process of loss of biological activity of protein due to unfolding of globules and uncoiling of helix by changing temperature of pH. By changing temperature or pH. Coagulation of egg white on boiling, curdling of milk are example for denaturation of protein. During denaturation, primary structure remains same. Secondary and tertiary structures are destroyed. Fibrose protein. These are fibers like proteins in which polypeptide chain are run parallel and held by hydrogen and disulfide bonds. Keratin present in hair. Wool, silk, myosin present in muscles. Globular protein. Proteins in which the polypeptide chains are coiled around to give spherical shape. Insulin and albumin are example for globular protein. Difference between fibrous protein and globular protein. Fibrous protein, they have fiber-like structure. They have spherical structure. About globular protein. Fibrous proteins insoluble in water. Globular proteins soluble in water. Peptide bond. An amide bond formed between two amino acids is called peptide bond or peptide link. Dipeptide means number of amino acids 2, number of peptide bonds 1. Number of amino acid n, number of peptide bonds n minus 1. Simple. A peptide formed by combining more than 10 amino acids called polypeptide. Insulin contains 51 amino acids. Main forces which stabilize the secondary and tertiary structure of protein: hydrogen bond, disulfide linkage, van der Waal and electrostatic force of attraction. Zwitter ion, the dipolar ion which neither move towards anode nor cathode under influence of electric field. This ion carries both positive and negative charge. The general structure of Zwitter ion. This is the general structure. Amino acids are classified into three types. Majorly, one is acidic, basic, neutral. Remaining two essential and non-essential. Amino acids contain two carboxylic acids group and one amino acid, aspartic acid, glutamic acid. Basic amino acid means amino acid which contains two amino group and one carboxylic acid group, lysine, histidine, glutamine. Neutral means the amino acid which contains one amino group and one carboxylic group, alanine, glycine, serine. Example. Essential means the amino acid which are not synthesized in the body are called essential amino acids. Example: valine, leucine, isoleucine, arginine, methionine, phenylalanine, lysine, threonine, tryptophan, and histidine. Non-essential amino acids. The amino acids that are synthesized in the body are called non-essential amino acids. Example: glycine, alanine, glutamic acid, aspartic acid, tyrosine, serine, cytosine, cysteine, and proline, aspargine, glutamine. Important point: optically inactive amino acid is glycine. Example for aromatic amino acid is phenylalanine, tryptophan. Heterocyclic amino acid is histidine, proline. Sulfur containing amino acid is cysteine, methionine. Alcohol amino acid serine, threonine. Phenolic amino acid is tyrosine containing phenolic OH. Amino acid proline. Nucleic acid. Complete hydrolysis of DNA or RNA yields pentose sugar, phosphoric acid, and nitrogen base. The sugar present in DNA beta 2 deoxy D-ribose. The sugar present in RNA beta D ribose. The nitrogenous base. The nitrogenous base present in both DNA and RNA adenine, guanine, and cytosine. The nitrogenous base present in DNA but absent in RNA thymine. The nitrogenous base present in RNA but absent in DNA uracil. Nucleoside, a unit formed when nitrogenous base gets attached to first position of pentose sugar is called nucleoside. Nucleotide, when nucleoside is linked to phosphoric acid at fifth position of pentose sugar is gives nucleic acid. Nucleotide are joined together by phosphodiester linkage. Next concept in biomolecules: vitamins. Vitamins are organic compounds required in the diet in small amount to perform specific biological functions for optimum growth and health. Water soluble vitamins, B group vitamins, and vitamin C. Fat soluble vitamins, vitamin A, D, and E and K. Why cannot vitamin C be stored in our body? Because vitamin C is water soluble, therefore it is readily excreted in urine. Name the water soluble vitamin stored in our body. Vitamin B12. Name the vitamin. Vitamin A, deficiency disease, night blindness. Vitamin B1, beriberi. Vitamin B2, digestive disorder. Vitamin B6, convulsions. Vitamin B12, pernicious anemia. Vitamin C, scurvy. Vitamin D, rickets. Vitamin E, muscular weakness. Vitamin K, increased blood clotting. Hormones, intercellular messengers are called hormones. Iodine containing hormone thyroxine. Low level thyroxine leads to hypothyroidism. High level thyroxine leads to low level high level hyperthyroidism. Important types of hormones and their functions. Note this tabular column. I hope you understood this video. Thank you for watching.